Hello, chemical systems. So this video is going to be about a few things: chemical formulas, structural formulas, and Lewis structures. Um, there's going to be a lot of stuff thrown at you in the videos today. I don't want you to get overwhelmed. Today we're going to focus on we're going to focus on chemical formulas. I'm going to introduce structural formulas and Lewis structures to you guys, but I'm not going to have you're not going to do any classwork. You're not going to have any quizzes on those two topics. But I still want you to know what they are. So when you watch today's videos and tomorrow's videos, you know what they're talking about. So chemical formulas, and this is directly from the definition from CK12, are elements in a compound are represented by their chemical symbols, and the ratio of different elements is represented by subscripts. So what do I mean by all of that? Well, let's go through some examples here. So first example here is oxygen. Whoops. I'll show you guys that in a second. Let's see. So this is oxygen is O2. And so if you get, well, actually, I'll go and pull out the periodic table there. So oxygen, that's the letter O. And you might notice it's the letter 2 at the bottom. That's called a subscript. If it's up on top right here, it's called a superscript, but we don't have that. It's a subscript. That's not going to let me undo my changes. Here we go. So the 2 means that in this molecule, there are 2 oxygens. So when we breathe oxygen, that's the form of oxygen we breathe is 2 oxygen atoms that are bonded together. And that's diatomic oxygen or gaseous oxygen. There's actually other forms of oxygen. O3, for example, is ozone, which is actually not good for you, it's poisonous, but it's good that we have it in our atmosphere to protect us from some of the UV rays in the sun. Another example here is H2O. You might recognize that. That's used everywhere for water. So that means that is a molecule with 2 hydrogen atoms and 1 oxygen atom. And another example here that's pretty important, NaCl. We studied that's sodium chloride. We studied sodium chloride when we looked at salt. So sodium chloride is made of one salt atom, or one sodium chloride molecule is made of, let me back up. One salt molecule or one sodium chloride molecule is made of 1 sodium atom and 1 chloride atom. So you notice here that this is why capitalization is so important when it comes to elements. If an element has more than 1 letter, for example, sodium and chlorine both have 2 letters. First letter is always capitalized, and the second letter is always lowercase. Same with chlorine. C is uppercase, L is lowercase. The reason is because when we put these elements into a chemical formula, we know where to start the next element. In fact, I think it wasn't too long ago before they started naming or giving a lot of the heavier elements proper names, that it wouldn't be uncommon to have something like UUM be one element name. We're not going to deal with anything like that, especially because, like I said, they've all been given proper names now. But NaCl, that's a chemical formula with 2 elements. And I know it's 2 elements because Na is 1 element, Cl is the next element. So capitalization is important. Make sure anytime you use a chemical formula, make sure your chemical symbols are capitalized where they should be. So O is capital because it's oxygen, H, hydrogen, O, oxygen. And we talked about NaCl a lot. Okay. So Lewis structures, a Lewis structure shows a chemical symbol surrounded by their valence electrons. What am I talking about there? Well, let me show you. And again, chemical formulas, the slide that I just went over, you guys are going to be doing a lot of work with that, but you're not going to be going through anything with Lewis structure. But let me show you what a Lewis structure would look like. I'm going to start with hydrogen. Hydrogen has 1 valence electron. So to represent hydrogen, I just write H for hydrogen, and then I draw a little dot, if I can manage a dot with my finger. for its one valence electron. And I'm also going to do oxygen. Oxygen has 6 valence electrons, so 1, 2, 1. Oh boy, 1, 2, 3, 4, 5, 6. So why am I drawing valence electrons in this fashion? So there's a whole set of rules about which electrons to draw first and where to draw them, which is why we're not going to go over them because there's a lot of rules. I'm going to draw another hydrogen over here. And actually, there's going to be another video. But all we're doing here is we're just representing the elements with their valence electrons. Remember, valence electrons is what? Can you remember? Valence electrons are the electrons in the outer shell of an atom. So it just so happens that oxygen is element number 6, so it only has 6 electrons. I'm sorry, no, oxygen is element number 8. So it has 2 electrons in the inner shell and 6 electrons in the outer shell. But this is why Lewis structures are important, because tomorrow we're going to start studying covalent bonds, and Lewis structures help us understand where these bonds are made. So the bond between hydrogen and oxygen are made here, and the hydrogen oxygen bond is made here as well. So hydrogen really wants to have an extra electron. So it shares an electron with oxygen. Oxygen would really like to gain 2 extra electrons on it in its valence shell. Remember the octet rule. It's not something we went over really for very long. The octet rule says that all atoms wish they could have 8 electrons in their valence electron shell. Well, oxygen has 6, so it only needs 2 more. So it shares its 2 extras with 2 hydrogen atoms. So this particular molecule I made has 2 hydrogen atoms. So H2 and 1 oxygen atom. So this is how water would make its chemical bonds. Would make its covalent bonds. Remember, ionic bonds is a transfer of electrons. Covalent bonds, which we're going to get into tomorrow, is when 2 atoms share electrons. So lastly, structural formulas show the chemical symbols with a general or maybe a more specific bonding structure. So let's take our example of water and just redraw it as structural formula. We just kind of simplify. Instead of drawing 2 valence electrons to show that what oxygen and hydrogen are sharing, we just draw a line. So anytime you see a structural formula, each line represents 2 electrons. So that's important to remember, that I have 2 electrons shown by that one line there. So that's what a structural formula could look like. Sometimes on these structural formulas, they also include the paired electrons. When I say paired electrons, I mean the electrons are already in pairs. So again, electrons like to pair off with each other, whether it's in a bond or whether they're already paired off previously. That's why we're not going over the rules of Lewis structures and structural formulas. But I just wanted to let you know what you're seeing. When you see these dots, those represent electrons. When you see these lines, each time you see a line, that represents 2 electrons in a bond. And I'll go over that more in a video tomorrow. So just to finish off, let's just go over a few more examples of structural formulas. Let me get my mouse back out here. So salt. So we don't draw since salt has an ionic bond, we don't draw salt with a line. We just say NaCl. Water, we just did an example of what water looks like. The HOH. Even though realistically, I wish I could undo that. Come on, where's my eraser? You can tell I'm an expert at this, can't you? HOH. Realistically, water has more of an angle like this. Anyway, another structural formula would be something like sucrose, which is just table sugar. So salt, table salt is NaCl, really simple formula. Table sugar, C12H22O11. So I have 12 carbon atoms, 22 hydrogen atoms, and 11 oxygens. The chemical formula doesn't really tell me much, which is why some people prefer a structural formula, which looks like this. So molecules can get pretty crazy. We're not going to go over how we know where each of these bonds would go or what each one of these symbols and lines mean, but I do expect you guys to know by looking at this chemical formula here at the bottom. By looking at this chemical formula right here, I do expect you guys to know that, okay, table sugar has 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. So this is one single molecule of sugar. Salt, on the other hand, that's what a single molecule of salt looks like. Since salt is an ionic compound, it's kind of unfair to say, well, that's what a single molecule of salt looks like. But because really what's happening is that salt joins up with sodium and chloride, joins up with a bunch of each other to make this crystal lattice. And you guys saw that one of your assignments where you saw salt was beginning to make all these shapes together. But anyway, I'm not going to make a mess on this page. So that's just the basics of Lewis structures and structural formulas. And again, what we're really going to focus on is this. We're going to focus on the chemical formulas, how to understand what those means. And to understand what those means, you need some understanding of the periodic table, how to use it. I hope you've bookmarked or maybe even printed out your own copy of the periodic table so you know where to find the names of these elements. So in the coming week, we're going to go over covalent bonds, understanding how covalent bonds are made and when they're made. And just looking at some common examples of covalent compounds. And covalent compounds are just molecules that are made with covalent bonds. So go ahead and go through today's material. If you have any questions, let me know. I'll talk to you later. Bye.